So what we're going to take a look at here is some properties of exponents. It's going to kind of kick off what we're doing in chapter 6. All of these properties that we're going to have to go through and use are here, so I recommend you copy down the names of all the properties because that's how we're going to refer to them, and then also what the actual rule says along the right-hand side for that name. Now, all of these should look relatively familiar. You guys have worked with them before in Algebra 1, and you guys even before Algebra 1 have worked with these kinds of different properties in some of your math classes. So you can pause it, you can take a look at this, but this is also in your textbook. It's going to be a very valuable resource. What we're going to do, at least for the rest of this video, is I'm going to kind of show you where these rules come from and their, the reasoning behind them, how we ended up coming up with these rules for all of these different things. Now, our first rule, looking at this, what it's saying, product of powers. Looking at it, which was just first rule up here. If I'm multiplying two things of the same base, it's essentially like adding their exponents together. For example, if I look at 2 to the second times 2 to the third, if I look at this and I try to expand these, I'm going to write this 2 squared as 2 times 2. And I can multiply that by 2 to the third, which would be 2 times 2 times 2. Looking at those terms all here, if I combine these 5 and I try to condense them down, what that's really going to be writing is 2 to the 5th. 2 to the 5th is saying 2 times itself 5 different times. 1, 2, 3, 4, 5. That would be 2 to the 5th. And really looking back up here, that's essentially the same exact thing as going through and just adding those two exponents together. This is going to work for numerical expressions, and all of these rules are going to work for algebraic expressions as well. So for example, this one I could go through and say, well, I know that's going to end up being 32. Another kind of example is if I had an algebraic expression like x to the third times x to the 7th. Looking at that, the same rule is going to apply, and I would go through and say I have two things of the same base. I'm going to add those exponents, so I could really simplify this down to x to the 10th for this rule. Next rule, looking at this, now what I have is I have some base raised to an exponent and then raised to another exponent on the outside. And what that's going to end up looking like is taking that base and its exponent being the product of the two bases, of the two exponents. So for example, if I take a look at, let's say, 2 squared on the inside of the parentheses, and we're raising that entire expression to the third. Now, kind of going about the same process as we did on the last slide, this is essentially the same exact thing as taking whatever's on the inside here and multiplying it by itself 3 times. So I could say 2 squared times 2 squared times 2 squared. Now, looking at all of these, this rule should look very similar to the last one we did. We're multiplying things together that all have the same base. So if I'm going to go through and do that, I'm going to add the exponents together. So I could say my base is 2 for all of them. I'll add the exponents, which would give me 2 to the 6th. Now, looking back at our original expression, that's really the same exact thing as saying multiplying those two exponents together. What we call this is a power raised to another power. And right from the start, we could go through and say, all right, that's really going to be the same exact thing as 2 to the 6th. In terms of an algebraic expression, if I had x to the 4th raised to the 10th power, I see power raised to another power. I'm going to go through, multiply those exponents, and I'm going to end up saying that's going to be the same exact thing as x to the 40th for that. Next one, what I have is two terms, a and b. They could be numbers, they could be anything really. They could be algebraic expressions, they could be a mix of both. And they're both inside the parentheses multiplied together, raised to some exponent. And what we're going to end up seeing is it's kind of like distributing the exponent into the exponent of everything else. So looking at a term like this, let's say we have 2 times 3 to the third. All right, looking at this expression, what this is really saying, like in the last few examples what we went through and did, is really saying 2 times 3 times itself, 3 times. Now, looking at this, to combine that very first rule that we looked at, if we're multiplying things of the same base, we add those exponents. All of these expressions have an exponent of 1. So, looking at it, I can combine all the 2's and add those exponents, which would give me 2 to the third. And I can go through and do 3 times 3 times 3, which would give me 3 to the third. Now, kind of backtracking to up here, what that looks like is saying, all right, well, that's really the same exact thing as distributing the exponents of both of these, saying 2 to the third and 3 to the third. And again, just like every other rule, this is going to work in this situation as well. You know, I have 2 and I have an x. The 2 gets distributed to each of these. It goes to the 2 and it goes to the x. So I would say 2 squared and x squared. And when I go through and I simplify that, I could say 4x squared. Because what you guys are going to see in class is anytime we have something like this, 2 to the third, 3 to the third, we're going to go through and we're going to actually plug that in our calculator and figure it out. You know, what is that actual number, if we can figure out what the number answer is actually going to be. You know, in an example like this, you know, 4x squared is the farthest we can go. All right, 2 quick ones. I'll actually start on E. Looking at this one, anything raised to the 0th power is always going to be 1. So if I say 4 to the 0th power, that'll be 1. I could say x to the 0th power, that's going to be 1. No matter what it is, it's going to be, if it's raised to the 0th power, it'll be 1. Now, a key one is this negative exponent, this idea of that. Anytime you see a negative exponent, what you're going to end up going through and doing is you're going to flip it over the fraction bar to make it positive, because we don't like the negative exponents when we go through and we simplify these, so that's going to be one of the steps that we want to get rid of. What that's going to look like is, you know, the base is going to stay the same, and so does the exponent. The only thing that changes is it flips over the fraction bar and our sign becomes positive. So for example, if I had 4 to the negative second, what I would go through and do is I would say, well, I see the negative exponent, I'm going to flip it over the fraction bar to make that positive. Now from here I can go through and say, well, I know what 4 squared is. That's 16, and I kind of can reduce that to this 1 over 16. Same idea here. Alright, if I have a negative exponent in the denominator, what I'm going to go through and do is I see the negative exponent, I'm going to flip it over the fraction bar, that entire term, the x to the negative 4th. So this entire piece here would move up to the top, and what it would end up looking like would be x to the positive 4, because when you flip something over the fraction bar, the exponent sign is going to change between negative and positive for that. And that one's going to be a key one moving forward when we look at simplifying various expressions. Next one, when I'm dividing two things of the same base, I'm going to subtract their exponents. So we'll look at an example. If I look at 2 to the 5th over 2 squared, I'm going to go through and I'm going to write this in expanded form like I have a few other times. 2 times 2 times 2 times 2 times 2, all of that being over 2 times 2. Now what I can go through and do is I look at this as a fraction and I see, well, I have a 2 on the top and a 2 on the bottom. If I have 2 over 2, that reduces to 1. So I can just cross these out because they're going to cancel one another. Same thing with these two. I have a 2 over 2. Those would reduce to 1. What I'm left with is 2 to the third. I have 1, 2, 3 2's. If I write that in condensed form, that's going to be 2 to the third. Now looking back to what we had originally, that would be the same thing as just going through and figuring out that, all right, well, what is 2 to the third? You know, we're going to end up saying, well, that's going to go all the way down to 8. Now, the same thing's going to apply if I had, x to the 7th over x to the 2nd. I'm going to go through and say, well, I'm dividing things of the same base. I can subtract those exponents, and that would come out to x to the 5th for that one. Same idea. Dividing things of the same exponent or same base, I'm going to subtract those exponents. Last but not least, if I have some fraction, say 4 over 9 squared, what that's going to end up being like, again, it's going to be like distributing here. I'm going to distribute that 2 to the 4 and to the 9. Same idea, 4 over 9 squared is the same exact thing as 4 9s times 4 over 9. If I went through and just multiplied these two fractions, I would multiply the top, which I can just say is 4 squared, and I can look at 9 times 9 is just 9 squared. And if I look at this from the beginning, that would be 4 over 2 and 9 over 2. That's who would get given to the 4 and the 9. We would distribute it to both of these terms. Same concept here. If I have x over y to the third, I would distribute the 3 to the x and to the y. I would say x to the third, y to the third. That's going to be another key one that we're going to see come up a lot. Now, these proofs aren't going to be as important to know, but as the rules are, because what you're going to do is you're going to be given an expression, and you're going to have to just mix and match and say, all right, what rule goes here? What do I, when do I use power of power? When do I use product of power? When do I use quotient of power? All these different rules, and there's going to be different ways to go about using them, but we have to have a fundamental and really solid knowledge on these and understanding these and knowing these.